Welcome, ladies and gentlemen. Let's begin our discussion for today. In just a minute, I'm going to be calling on you to share your responses for whether each given letter was an expression, an equation, a formula, or if there was some overlap. All right, so let's go ahead and take a look at the first one. Is the first one an expression, an equation, or a formula? Matthew with one T.
An expression.
An expression, good. So we've got a collection of variables, numbers, and operations, but no equal sign. So this is an expression. Great. What's different then about letter B? Don't call out. What is letter B then? Carson?
I got an equation.
Equation is correct because we've got two expressions, right, set equal to one another. And yet, this equation is also a formula. What is it that makes it a formula? Well, because it's a single variable solved for, written in terms of one or more other variables. And so because that's an x equals, and then it's given by, right, one or more other variables, and x doesn't appear again, that is both an equation and a formula. In order to be in the running for a formula, it has to have an equal sign. It has to be an equation. So all formulas are equations. And yet, not all equations are formulas. Take a look at letter C. Is letter C an equation, Katie?
Yes.
Yes. X equals 15 is an equation because of the equal sign, right? And yet it's not a formula. Why is it not a formula? Because the variable x is not given in terms of one or more other variables. It's just a single value, 15. So it's not a formula the way that letter B is a formula. Do you see that? So my requirements for equations have to have an equal sign. Two expressions that equal to one another, that's an equation. In order to be a formula, it's got to be one variable written in terms of one or more other variables. That's what makes it a formula as opposed just to a plain Jane equation. Does that make sense? Awesome. So go ahead and quietly tell your partner, letter D then, and be ready to share with the whole class when I call on you. So quietly decide with your partner, and then I'm going to call on you. Okay, so which of these descriptors, expression, equation, formula, right, best represent letter D? What did you guys say? Michael and Tyler?
We said it was a formula, but we also said it was an equation.
A formula and an equation. Raise your hand if you and your partner had the same labels. Correct. That is both an equation and a formula. The equation is a giveaway because of the equal sign, and yet it's only a formula if it's one variable solved on one side instead equal to one or more other variables. Do you see it? Good. All right. E, equation, formula. Only an equation, not a formula. Wait a minute. Aren't there one or more variables, right, on the other side? Yes. But there's one or more variables on the left side, too. It's not a single equation solved for, right? Solve for it on one side and then set equal to one or more other variables. In fact, this is just an identity here. A plus B is the same as B plus A. This is not a formula. It's only an equation. And lastly, expression, equation, formula. Go ahead and share with the whole class. Colton, expression only. Raise your hand if you got expression only for F. Way to go, you guys. Let's take a look at number 2. We can evaluate that expression for particular variable values for A and B. We want to make sure we're careful with our order of operations, right? We can't escape them. Pemdas, please excuse my dear Aunt Sally. And to avoid making mistakes, I strongly encourage you to use parentheses when you do the initial substitution. If you use parentheses, anytime you sub in for our initial variable value, it's going to reduce the chance of you making a mistake. Let me show you what I mean. I'm going to rewrite 5b minus a plus 2a squared. But I'm going to put parentheses everywhere I see my original variable and replace it with the given variable value. So where I see a b, I'm not going to put b, I'm going to put 2. Everywhere I see an a, I'm not going to put a, I'm going to put -1. Now we can go ahead and use our order of operations. Pemdas, please excuse my dear Aunt Sally, right, to make sure that we get the correct result. So watch your negative signs. Here we go. 5 times 2, that's multiplication, that's 10, minus the negative 1. Subtraction is just adding the opposite. So minus negative 1 is the same as plus a positive 1. Another way to think of that is negative times negative is positive. Everybody see that? Plus, and there's a battle going on right here, right now, between this 2 out front and this 2 up in the exponent. In the battle between exponents and multiplication, who wins, right? Who wins in my order of operation? Forrest? Exponents every time. And so we must first square the negative 1 before multiplying by that 2 factor out front. Once again, exponents come before multiplication. Forrest tells us correctly, so we will square the negative 1 and then multiply by 2. Another reason I went with parentheses is because it emphasizes what value is being squared. What number is being multiplied by itself? Negative 1 is being multiplied by itself. Negative 1 times negative 1 equals positive 1. So whenever I square a number, the result is non-negative. If you put in your calculator negative 1 squared with no parentheses, it'll spit out negative 1. Right? Is that correct? Well, your calculator is doing 1 squared, exponents first, and then timing by a negative to get negative 1. Your calculator is just doing what you're telling it to do. That's why I encourage you to use parentheses. Negative 1 quantity squared is positive 1 times the 2 out front. All right, in any case, we get 10 plus 1 is 11. Plus 2 is, dun, 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 dun. Our final answer, 13. Thanks in advance for your honesty. Raise your hand if you got 13. Everybody get the positive 13? You did. Yes, that's great. Okay, hands down so you don't. Good job. Let's go ahead and take a look now at our simplification. There's no evaluation here. We're not plugging in variable values, right? We're going to just follow the order of operation. And yet, I saw no less than 3 different responses for number 3, right? As I was walking around the room. We got all kinds of different answers for number 3. And yet, mathematics is supposed to be that confident, right? We're all supposed to get the same thing if we're simplifying that numerical expression. We should all get the same thing. That's why we have our hierarchy in our order of operations. So let's go ahead and see if we can't all figure out what the single correct answer is for this simplification. All right, let's go to our Pemdas. What does the P stand for in Pemdas? AJ?
Parentheses.
Parentheses. Are there any parentheses to evaluate? So I don't have to do any parentheses evaluations. So what does the E stand for? Don't call out. So what does the E stand for? Isabel?
Oh, excellent.
Exponents. Are there any exponents to evaluate? No. So already to M. So what does the M stand for, Lucas? Multiplication. Multiplication. So we do multiplication, and that's misleading because M and D are really on the same level. Multiplication and division are on the same level in my hierarchy for order of operations. And the A and S, addition, subtraction, I do those last. All right, so let's go ahead and sort this out. If both multiplication and division occur in the same problem, I perform the operations in order from left to right, like I read a book. So let's go ahead and see. I have both multiplication and division in the same problem, so I perform my operations in order from left to right. So I first do 16 divided by 2. I do that before I do the multiplication by 4. This is not 16 divided by 2 times 4 is 8. It's not 16 divided by 8. Does everybody see that? It's 16 divided by 2 is 8, then times 4 minus 10 plus 5. Now I just have multiplication, so I do that first. 8 times 4 is 32, then minus 10 plus 5. And now I'm down to addition and subtraction. I do those in order from left to right. 32 minus 10 is 22, plus 5 is 27 something. I'm getting 27 for my final. Raise your hand if you did as well. Anybody else get 27? Yes! You guys are doing great. Oh, it's going to be a great semester. It's going to be a great semester. Thank you for having your binder ready. 4 points for checking after the weekend. So next class, not today, next class we'll check your binder. And remember that Bellwork and notes, first label divider, activities, second label divider, assignments, third label divider. All right, you guys are awesome. let's go ahead and grade our first homework assignment. You've already shown me if you're eligible for the reading question point. Yes, that's right. This 1 point, this +1, was for completing the reading questions as part of your assignment, and that was the purple log. If you showed me you're completing reading questions, then you're eligible for that +1, right, after we get your completion score. If you didn't do your reading questions, then you would add on 0 to your book problem, or to your regular homework problems. Excuse me, but for this time and this time only, we're going to let you do those reading questions because there's some confusion as we rushed towards the end of the bell on that first day because it was the first day of class. You'll be able to complete the reading question on the reading log and show me on Tuesday, still for full credit, but you have to remember to show them to me and we can add that 1 point back in. It doesn't change today though. Today it's going to be a +0 when you do your, when you add on for the reading questions. This will stay a 0 if you didn't know them today. But our regular problems are worth 4 points in Infinite Campus. And so today, there were 23 problems on my worksheet. We do homework based on completion, right? Based on completion, so if you try each problem, you showed your work to the best of your ability, you can get full credit in Infinite Campus. Then you go and check it with the posted answer key online and make corrections. You may do that in pen, you may do that in pencil, right? Either way is fine so long as you completed your assignment and checked it before you come to class. So the expectation is that you're not only completing the assignment, you're also checking for accuracy. Otherwise, it doesn't do any good. That's the point of homework, is to practice, but you have to be practicing correctly. So in order to get full credit on your homework, you have to complete it and check it before you come to class. However, your grade in Infinite Campus is a reflection of that completion and checking. It doesn't matter if you got 12 out of 23 correct, right? So long as you did all 23 and checked them, you're going to get 4 out of 4 for your problems, and then plus a possible 1 if you did your reading questions, bringing your total for assignment number 1 to 5 points possible. So what you're going to do is, once again, give yourself credit for those you completed. I did all 23, right or wrong, and check them. Out of 23 problems on this assignment, divide, enter, multiply by 4. And then if you did your reading question, you add 1 to that. If you didn't do your reading question, you add, questions, you add 0 to that. And then you box your Infinite Campus score nice and big on top, round to the nearest half. And so if you got 4.333, that would round to 4.5. Don't put 4.333, put 4.5. If you got 4.666666, right? Then that's 4.5 also. So you round to the nearest half point. If you got 4.75, that rounds to 5. Okay, so you're going to round to the nearest half point and box it nice and big on top. Everybody good? So I did all the problems? No? What?
I'm confused.
Okay. So how many problems did you do?
All of them?
Great. So you get 23 out of 23. Right?
Yep.
Divide, enter. I get 1. Times the 4 is 4. Did you do your reading questions?
Yeah.
Yep. Plus 1.
Okay.
So you put 5 and you box it. If you did all your assignment but not the reading questions, you put a 4 and box it. If you did 10, right? If you did 10, do you have your calculator out? Isabel, if you did 10, I know you didn't do 10, but if I did 10, you do 10 out of 23 is what?
0.43.
0.43, right? Times 4.
1.74.
1.74. 1.74 plus I did my reading questions is 2.74. What am I going to put on my paper?
3.
No! 2.5, because 2.74 is closer to 2.5. I'm going to put 2.5 and box it. Great question. In a good way, a positive constructive way. Thank you.
Oh, it's okay.
I appreciate you. We're all learning. Yes? Everybody good? You're good?
Yeah.
Everyone at this stage should have their name on top and a box into the campus score. Now we're going to pass them in, but we're going to keep them in the same columns, right? We're going to keep them in the same columns because I passed them back to you next class. So you're going to pass from the back to the front and keeping them in the same columns. Don't turn in the purple sheet. You need that for assignment number 2. I only want worksheet number 1 with the box into the campus score on top. And you're going to pass from the back to the front, keeping the same column. Front rowers, please make sure they're facing the same direction with name on top. Staple on the same side. It makes it way easier to record and get back to you in a timely manner. So thank you for your help. Thank you, Lauren. Everybody good? Thank you, ladies and gentlemen. We'll get better at that process as time goes on. I appreciate your help. Okay, so we've taken care of our worksheet. Feeling good about that. Today we've got a slew of content objectives. The good news is that we've already laid the groundwork for a lot of these last classes. We investigate our solving equations. Today, you can see from our agenda, we're going to rewrite formulas. We're also going to work with functions and notation, which will include some evaluation of functions, as well as solving equations, and then some more solving specials. And so we saw some special equations where you were solving and all of a sudden, bam, there were two paths, there were two sets of arrows where before there was only one. So we're going to take a closer look at equations that have multiple solutions, and we're going to do that today. So we've got lots to do. Let's get going. First off, let's take a look at, from our Bellwork, we saw some of those equations were formulas, and some of them weren't. So what does it take to be a formula? An equation in which one variable is written in terms of one or more other variables is called a formula. V equals pi r squared h is a formula of V in terms of R and H, because V is the variable that's solved for, alone on one side, and written in terms of one or more other variables. That's what makes that a formula, just like our Bellwork. What we're going to do is use our knowledge of solving equation as a process, right? As a process of reasoning, our reverse and undo. Our forward steps to get our solving steps, we're going to do that in order to solve a formula for a different variable, and that's what we'll call rewriting formulas. So let's go ahead and solve this formula, V equals pi r squared equals h. Let's solve it for h. So we can do that if we focus in on our problem. It looks like h is over here on the right-hand side. What operation is going on between h and the pi r squared right now? What operation is going on between the h and the pi r squared right now? Lucas? Multiplied, right? So right now my h is being multiplied by pi r squared. Whether this was equal to v or whether it was equal to 17. Tell the class when I call your name what operation undoes multiplication. Caden? Division. And so in order to solve for h, we're going to undo that multiplication, and we'll do so by division. So we'll divide both sides by pi r squared. We can do that in one fell swoop. That will get h by itself. And now we'll rewrite h in terms of v and r. My final answer would be h equals v divided by pi r squared. That's it. We've rewritten that formula for h in terms of v and r. My original was given a formula for v in terms of r and h. So that's just kind of the jargon that goes along with formulas. Awesome. Let's try another. Let's solve the formula a equals 1/2 h times quantity b sub 1 plus b sub 2. Let's solve that for h. Firstly, I want you to go ahead and talk to your partner and see who recognizes that formula from geometry. Who recognizes that formula from geometry? Gosh, it looks kind of familiar. Who's that bugger? Okay. Raise your hand if you and your partner agree. You think you know what formula that's referring to in geometry. What geometric formula do you think that's referring to? Thanks, hands down. So what do you think, Lexi and Colton?
Area of a trapezoid.
Area of a trapezoid. Who else thought area of a trapezoid? Yes, area of a trapezoid with parallel bases b sub 1 and b sub 2. All right, let's go ahead and solve that formula. Let's solve that formula now for h. Okay, let's consider our operations that are going on right now. So if I want to solve that for h, right now, h is on the right-hand side, and it's currently being multiplied by 1/2, right? And multiplied by b sub 1 plus b sub 2 in parentheses. So I'm not going to distribute here to get rid of the parentheses because the variable I want, h, isn't hiding inside those parentheses. It's not tied up inside those parentheses. And so I don't want to distribute through the parentheses. I want to leave those parentheses together because then I have less stuff to do. Instead, I want to get rid of that fraction first. What undoes right? That fractional coefficient, what undoes multiplying by 1/2? Well, dividing by 1/2 undoes it, but dividing by a fraction is the same as multiplying by the reciprocal. So the best first step in this case would be to multiply both sides by 2/1, the reciprocal. So I'm going to multiply both sides by 2. When I do that, I get 2a equals h times quantity b sub 1 plus b sub 2. Now I'm trying to solve for what? Keep my eye on the prize. I'm trying to solve for h. And right now h is being multiplied again by quantity b sub 1 plus b sub 2. What operation undoes multiplication, Michael?
Division.
Division. So I'm simply going to divide both sides by quantity b sub 1 plus b sub 2. Because the fraction bar implies quantity, I really don't have to write the parentheses. In fact, in my answer, I won't. But I want you to see where that's coming from. This gets the h alone, and my final answer would be h equals. On the left, h equals solve for. I know I'm rewriting a formula in terms of a and b sub 1 and b sub 2. I get 2a over quantity b sub 1 plus b sub 2. That's pretty sweet. There, I've rewritten the formula for h in terms of a and b sub 1 and b sub 2. Let's do one with pendulum. So, printable. The period p of a pendulum is the time in seconds it takes a pendulum to make one complete swing back and forth, and is calculated by using the formula p equals 2 pi times the square root of L over G. What? Where L is the length, okay, the length of the pendulum as measured in meters, and G is the acceleration due to gravity. And if we're working in metric, because we hear meters there for my distance unit, then that's 9.8 meters per second squared. That's my gravitational acceleration. Awesome. Let's go ahead and figure out what this formula is rewritten for L. So I'm going to rewrite this formula for L. In order to do that, I'm going to consider my inverse operations. Everybody, pretend for a moment that this wasn't a formula or an equation, but just an expression. So which side of the equation has my L in it? The right-hand side. So everybody, cover up the equals P. And let's pretend we were plugging in a variable value for L, like we were plugging in 7 for L. To evaluate that expression, what would we do first? So I'd plug in 7 for L, and I would do what first? Michael?
Divide by G.
Divide by G. So my first forward step would be divide by G. Then I would take the square root as my second forward step. Then lastly, I would times by 2 pi. Yes? Does everybody see? Those are my forward steps. So to get my solving steps in this more complicated example, I can reverse and undo those forward steps to get my solving steps. If the last thing I did was times by 2 pi, what's the first thing I'll do as I go to solve this? Lauren?
Multiply by 2 pi.
If
Or I mean divide, sorry.
Absolutely, I'm going to divide by 2 pi. Thank you. If my middle thing was taking the square root, what am I going to do to undo that? Jacob? To the... Absolutely. I'm going to square it or raise it to the second power. Perfect. And what's going to undo that division by G? AJ? Absolutely. Okay, guys, there's a recipe for success. Let's apply these inverse operations in red by solving steps in order. First thing, divide both sides by 2 pi. Here we go. Divide by 2 pi. Next, I get P over 2 pi equals. I divided by 2 pi, so I'm left with the square root of L over G. Next step. In red, square both sides, raise both sides to the second power. So my next step is to raise both sides to the second power. Everybody see it? Yes? When I square P over 2 pi, I'm just going to leave it as P over 2 pi squared. However, on the right, I've undone the square root, right? The square root squared gets me that quantity L over G inside the radical alone. I'm done with the radical now. I've undone the square root, bless you, by squaring. Are we good? Final step, bless you. Final step, Mason?
Multiply by g.
Heck yeah, we're going to multiply both sides by g. So we're going to multiply by g, multiply by g. Let's do it. On the left, I get g times quantity p over 2 pi squared equals L, and I've got, does that copy it for me? It looks great. Does that look great to you? It looks great. Let's try it anyhow. Not gonna let me. No. I don't know why. All right. So what do we get for that, Magnus?
G times parentheses p over 2 pi squared.
Awesome. We've solved for L in terms of P and G. Ready? What's the approximate length of a pendulum whose period is 5 seconds? How do I do that? I go ahead and find my period P and replace it everywhere I see it with a 5. Meanwhile, G is a gravitational acceleration. That's 9.8 meters per second squared. So I'll evaluate this and get 9.8 times 5 over 2 pi, all squared. If you use your calculator, make sure put parentheses around the 2 pi. Otherwise, it will divide by 2 and then put the pi on top. And we want the pi on bottom of that fraction. Everybody, let's try it. Ready? 9.8 times 5 over parentheses 2 pi close squared. Pinch of salt over the shoulder. I'm getting 6.206, right? And is that seconds? Is that seconds? What would a label for that be? Lauren?
Meters.
Absolutely. We just found L, the length. That's measured in meters. Nice job. So we want to make sure that we're putting that. And we have this evaluated my formula after rewriting it for L. Awesome. So rewriting formulas is a high leverage skill. It's something you're going to have to do in all your science classes, right? Particularly physics, right? Which is basically math in context, where we have values for all the variables in these formulas. So physics is a lot of formulas. You definitely have to do that. All right, let's go ahead and take a look at printable, our specials. And so we've got our special equations that I want to take a closer look at today. And those special equations are those where we could have multiple solutions. And so everybody remember our strategy. We can go ahead and cover up the equation and write our forward steps if we were just evaluating in middle school. What would we do first if we plugged in something for k? My first step would be square it. And so my first forward step would be squaring, followed by subtraction. Get ready because I'm calling on you. What are my solving steps going to be in order? Get ready. My solving steps in order are going to be what first? All right, what am I going to do first? Haley?
Add 8.
Good job. I add 8. And then what's going to undo squaring? Or what's going to undo squaring? Matthew?
Square root.
Absolutely. Except for one important difference. When we undo squaring, we need to consider two possibilities. Why? Because there's two numbers such that when squared equal a given result. You saw last class in your activity, when we took the square root of 25, what we were really doing is saying what number squared equals 25. And you guys all said 5, Mr. Fritz. 5 squared equals 25. And I said yes. But what other number multiplied by itself also equals 25? Right? Forrest? -5. And so there's two quantities such that when squared equal a given result. That's why you have to consider both the positive and negative result. All right, let's do it. First solving step. Add a to both sides. Do it. Do it. Awesome. Next solving step and last solving step, I undo squaring by considering the positive and negative square root. And so, all right, k squared equals blah means that k is given by the positive and negative square root of blah. In this case, blah was 36, so it does reduce. But either way, even if it didn't, I'd still have two answers. That's my two paths. I'd have k equals the positive root 36, and I'd have k equals the opposite root of 36 is -6. You see how we have two answers? Multiple solutions, and that's why we're calling that a special. Sweet house. And last special, absolute value. And so if I cover up the equation and pretend I had a variable value for q, if I plugged in something for q, like 3, what would I do first? I times it by 2. Yes, you guys see that? I times by 2 is my first forward step. Then I would take the absolute value. So then I take the absolute value. Then lastly, I would increase the value by 7. So everybody see, there's my forward steps. Now let's reverse and undo my solving steps. Here we go. What undoes addition by 7? Subtraction by 7. What undoes taking absolute value? Here's the new thing. We undo absolute value by breaking it up. That's when you split it into two arrows. One is the positive distance number, one is the negative distance number. And so I'm going to go ahead and call undoing absolute value as break it up. Break it up. And lastly, we undo our multiplication by 2 by dividing by 2. All right, let's apply our inverse operations in order. First step, subtract 7 from both sides. Do it. Next step is to break it up. What does that look like? So we're going to break up this equation now. We're going to break it up into two separate paths. Absolute value is defined to be the distance back to 0 on the number line. And so if my distance away from 0 is 18, what two numbers are a distance of 18 away from 0 on the number line? What two numbers are 18 steps away from 0? Magnus?
18 and -18.
Yes! Which is why I write whatever's in the bars, in this case 2 cubed, instead of equal to the positive number, instead of equal to the negative number. Magnus says that's 18 and -18. You're absolutely correct. That's how we break it up. There's our two paths. How many solutions will we have? Two solutions. We just keep on with our inverse operations for the final steps. So here we go. Divide both sides by 2. Divide both sides by 2. And we'll do a quick check. -9, my original for q. 2 times -9 is -18. Absolute value of -18 is +18. Plus 7 is, does that equal question mark 25? Yes, it does. I love math. So sweet. You guys are crushing it. Okay, so at this stage we've rewritten formulas, and we've also practiced solving equations. The remainder of our time, we want to work on new function notation, right? Evaluating functions, and then also some input and output terminology. So relations and functions was the topic for 1-2 in your reading. Functions are mathematical models of relationships between two variables. We're going to talk about what makes a particular relation a function or not in today's class and next class. Firstly, a relation is just a collection of ordered pairs. If we had some collection of ordered pairs, like points 2, 7, 3, 6, negative 2, 5, and 2, 3, that's a relation. A relation simply pairs inputs with outputs. A function is a special kind of relation in which each pairing, right, each input is paired with a unique output, one and only one output. Every time I put an input in, it must produce the same output result. Every time I put a 3 into my function machine, right, it has to produce 6. In this particular relation in green, we can determine if it's a function by considering all the input values. If the input values never repeat, then it's guaranteed to be a function, right? Because we don't have the opportunity for a single input to produce more than one output. However, as you scan this particular relation, is there an input, an x coordinate, a first value that repeats? Well, yes, there is. Right? What input value, what x value repeats? AJ?
2.
2. Notice how the 2, the first value in this ordered pair, shows up more than one time, which would be okay so long as it produces or is paired with the same output value each time. However, in the first case, the input 2 is paired with the output 7. In the second case, the same input 2 is paired with 3, a different output value. Therefore, this is not a function, right? This is not a function. In order to be a function, each input must be paired with a unique output, the same output every time. Every time you see a 2, it has to be paired with 7, right? That would guarantee this is a function. This input 2 is paired with more than one output. In the first case, 7. In the second case, 3. Not a function. What about now? What if I change that 2, that second 2, the problem 2, to a negative 2? Now is it a function? Lucas?
No,
How come?
because negative 2 is paired with 5, and then now it's paired with 3.
Now negative 2 appears more than once and is paired with multiple outputs. So now it's no longer, right, it's no longer a function either. So the only way to fix this would be if this was 2 paired with 7, and then we'd be good to go, right? Or if we now change this to something else like negative 12. Oh, I just gave it away. What if I change that to negative 12? Now is this a function? Yeah, no input values, no x values repeat. So it's guaranteed to be a function because each input occurs only once. There's no way that it can be paired with multiple outputs. All right, last thing. What if 2 is paired with 5? And 3 is paired with 5? And negative 12 is paired with 5? And negative 2 is paired with 5? Is this a function or not? Well, in order to be a function, each input, right, each time an input appears, it has to be paired with a unique output. This is a function, right? Because 2 only occurs once as an input value. Negative 2 only occurs once as an input value. Negative 12 only occurs once. So this is guaranteed to be a function regardless of what that second number is. It can be paired with 5 every single time, right? Each input can be paired with 5, and that's still a function. Consider the pairing, brand new relation. Ready? Consider the pairing. Wanakee High School student is the input paired with his or her grade level, 9, 10, 11, or 12, as the output. Would this be a function? No. Every time, right? Every time I put in Colton G, what am I going to get? 10, right? And I put in Colton G again, am I going to get 11 or 9 or 12? No. Every time I put in Colton G, I'm going to get, right? I'm going to get 10. Turn that around. All right. Now let's have my grade level as a number 9, 10, 11, 12 paired with output that's a Wanakee High School student. Well, now I've got all kinds of problems because I put in 10 once and it's paired with Colton G, but I put in 10 again and it's paired with Lucas G. And I put in 10 again, right? And it's paired with Mason? Yes? Okay, so you see how the same input 10 now is paired with multiple people? Yes? All right, not a function. We'll practice. We'll practice more. You have a chance to make up your own. Dependent variable value is the second coordinate, it's the y, it's the 5 in this relation. Independent variable is the input values. It's the x values, the first number in each pyramid. All of these notes are posted in the completed class notes on the file hyperlinked in Moodle, and so if you don't get something written down, right, don't worry, you can always just check out the completed class notes on Moodle. That shouldn't discourage you in any way from writing this down right now. I'm just saying, in the interest of time, if I move on a little too soon for you, that's fine. You can always go to the completed class notes, finish up. So I want to make sure we get to our stuff. Input is the value of the independent variable. It's all the x's. Input or x's come from the domain. They're within the domain of the function. Outputs are values for the dependent variable value, the y's, the outputs. Together, the collection of all those y values form the range. So y's are within the range. Oh, here it is. There's the domain. It's the set of all the allowable independent variable values, all the inputs. In the collection of all the dependent variable values, those are the outputs. Those are the y's. That's the range of a function. Once again, in the interest of time, I'm going to have to be scooching along here. But if you didn't get everything written down, you can always check out the completed class notes, which are already hyperlinked. A nice graphic organizer, right, shows that all the independent variable values, or the first row of a column, like when you make a T-chart, those are all the x's, right? In the order of pairs, that first number, those are all the inputs. They make up the domain. The dependent variable values are the second number in each of those points, or the right half of a T-chart. Those are the outputs, the y values, the dependent variable values. And one section to go, you guys. It's often useful to write our relationships in function notation or Euler notation. And so if we had the formula y equals 4x squared plus 7, we could rewrite that in function notation, right? Simply by replacing my output values, my y, with function values, f of x. That is to say, well, I better not do it because of mapping. That is to say, in f of x notation, we simply write f of x equals 4x squared plus 7. Y is equivalent to f of x. So to rewrite a formula in Euler notation or function notation, we just replace the y with f of x. In mapping notation, right? In mapping notation, we use colons and arrows, but it means exactly the same thing. It means we have a function that's named f that takes input values of x and maps them onto output values given by 4 times x squared plus 7. So in each case, we're just replacing y with its rule or with f of x. You have to know what mapping notation is, but far and away the most common notation is the function notation. Right? That function notation, Euler's notation, is more common than the mapping. Let's do some practice. So we're going to go ahead and, oh yes, we're going to go ahead and grab onto an input value, an x value, right? And the collection of all these input values, all these x values, if they were in a bucket, the name of that bucket would be the domain of that function. So I'm going to reach into my domain bucket and I'm going to grab an independent value, an x value. And I'm going to put it into my function machine. And when I put it into my function machine, it does some operations, squares and times it by 4, and then adds 7, and then spits out a y value, a function value, y equals f of x. And if I caught all of those y values in a bucket, what would the name of that bucket be? Well, the collection of all the output values would be the range of a given function. And so my x values are inputs, right? My y values are outputs. My y values are function values. And if I kept all those y values or function values or outputs together in a bucket, that would be the range of the function. Versus the possible inputs, right, are x values. Our x values are from the domain and they spit out y values into the range. And so this is a nice little graphic organizer. All right, let's go ahead and do some function notation. I can evaluate a function using function notation easily. In Euler notation, it's easy to see my independent variable. My input is inside the parentheses. In order to evaluate t of 20, all I'm going to do is replace the c, my input variable value, with 20 and evaluate. So t of 20 equals 1.8 times c plus 32. But what's c? C is 20. So 1.8, 3.6, 36, 39. Is that right? Does math work?
Yeah.
Tell me math works. Gosh, wouldn't that just be chaos if math didn't work, right? Buildings would start falling over, computers would go, okay, yes, math works. Good job, math works. So evaluating a function in Euler notation is easy. Inside the parentheses is my input variable value. We can do the same for mapping notation. Let's go to the function named f that accepts inputs of x and maps them onto outputs in accordance with the rule of square root of 5 squared minus input squared. If I took 3 and put it in for x, it would map it onto the function value given by square root of 5 squared minus 3 squared, which in turn is 25 minus 9, which in turn is the square root of 16, which in this case simplifies to 4. That's pretty sweet. We could even do it with expressions as inputs. Let's replace my input value, input variable x with 2w, right, with quantity 2w, and then rewrite it. Well, what will that be mapped onto? Well, f accepts x values and maps them onto function values given by 5 squared minus input squared. It's just that now my input is quantity 2w. So in there we'll have 2w, which means I have square root of 25 minus, and here's the kicker. Whenever I square something, I multiply it by itself, and that's why I encourage you to use parentheses. What's 2w multiplied by itself? Well, as an aside, I'm thinking that's 2w times 2w. What's 2w times 2w? Then it's easy to see why this is 4w squared, not 2w squared, 4w squared, because I'm multiplying 2w by itself. And that's as simplified as we can get. So 2w quantity squared means 2w times 2w, and that's 4w squared. Oh my goodness, we're almost there. Why did I say 45? Printable? Okay, so let's practice some. We're going to rewrite using the other notations. So we're going to do one together, and then you're going to do a couple with your partner, and then we're going to share. How would I rewrite the formula y equals in function notation? Easy cheesy. I replaced y with f of x. The rule remains the same. How would I rewrite a mapping notation? Easy cheesy. I'll take inputs of x and map them onto outputs in accordance with the rule 3 times input squared minus 5. We could still do y equals for the formula. In the second row, it's just my formula would be y equals square root of x, 2x rather, and then plus 7. That's the same. And it would map it onto outputs given by the same rule. However, now my function is named g, not f. That was the difference here I saw. Everything else was the same. So g takes inputs that are x and maps them onto outputs in accordance with the rule, square root of 2x, and then plus 7. MBD. Can we go backwards? Let's start at the mapping notation and work our way backwards. Here, I see a couple things. Firstly, bless you, my dependent variable values are a, right? Not g, not f, but a. And so my function notation is going to have not f or g, but a. What's my input variable? K. And so my function notation is not going to be f of x. It's going to be a of k. There's my input variable. Inside the parentheses is k. It's the variable that's in my formula. And what's my formula? K squared over 8. Instead of having y equals this time, I would probably go so far for my formula as to have a equals k squared over 8. Is probably what I'd write. You could also do y, but I think it's pretty sweet to write k squared over a equals k squared over 8 because it was a for the name of my function. Carson? Oh, classic teacher fake out. I'm drawn to that kind of thing. Is that a raising? Is that a raising? No, just stretching. Let's do some evaluation. Ready? I want you to take your input of 8 and plug it into G and check with your partner. So everybody try now, and I'm going to pause the recording while you guys work that out. Okay, ladies and gentlemen. And so for my first evaluation, G is going to accept an input of 8 and map it onto what rule? So what did you do for the first one? What did you do for the first one? Katie?
So you're gonna do G substituted with 8, so that equals the square root of 2 times 8 plus 7.
Awesome. The first step, that evaluation, that substitution, right, is the most important part. We want to make sure we're putting in the correct value into the correct place, and then it's just Pemdas. Now we just do our order of operations. We multiply first. We square root second, so that's going to be 4 plus 7. And I saw lots of 11s when I was coming around. That's good news. Raise your hand if you got 11 for the first one. Awesome, and thanks for your help. Good job. Let's take a look at the second one. This time I'm going to take the input -3, and I'm not going to put it in to G's rule, right? Where am I going to put it? Jacob? Where am I going to put -3 in that second row? Absolutely. I'm going to put it right in there in F's rule for the x squared. I'm going to replace the x with -3. Let's write that once. Ready? 3 times -3 squared minus 5. That's the most important part, getting that substitution right. Now I just do order of operations. Keep in mind that the battle right here is between the 3 multiplying the input -3 and the 2 trying to square the input -3. Who wins in the battle of multiplication versus exponents? The exponent. So I have to do -3 squared, which is positive 9. Right? Positive 9 before I ever do the times 3. That gives me the 27. Minus 5 last. And that gives me 22. Raise your hand if you got 22 already for the second one. Anybody get 22? Yes! Good job, you guys. That's great. And finally, the best for last. Yes, that's right. The F word. No, Colton, not that F word. Fractions, right? Fractions. Rear their ugly head again. We need to be able to evaluate an expression using fractions without using our calculator every time. So how can we do that? No problem. I think it's easier to do this without a calculator. We'll go ahead and evaluate. A's rule says take an input and square it. What's my input? In this case, it was 3/4. So let's do that. Let's do 3/4 squared. What's that? Well, that means 3/4 times itself. 3/4. So on top, I'm really doing 3/4 times 3/4. And I'm doing that before I ever did the 8. 3/4 times 3/4 is 9/16. And that's still all over 8. And dividing by a fraction, dividing by a quantity is the same as multiplying by its reciprocal. That is to say, dividing by 8 is the same as multiplying by 1/8. And I'm doing this all without a calculator. However, I'd have a hard time sleeping tonight if I left it that messy. This was 9/16, all over 8, much better. So this is equivalent to 9/16 times 1/8, which is how we get our final answer. Straight across, 9 times 1 is 9. 16 times 8 is 80 plus 48 is 128. I think 128. If you did this in your calculator from the very beginning, you should be able to do math, frac, enter at the end, and it should spit out 9 1/28. That's pretty sweet. All right, ladies and gentlemen, let's close it up for the day and make sense of your new learning. So right now we're going to do, oh no, we have one more solving. Let's do one more solving, sorry. For what values of x does f of x equal 13? Well, we're not going to put in 13 right here. Oh no. Does x equal 13? No. F of x. F of x equals 13, so we're going to put 13 right there and then solve the ensuing equation. This is a very important problem. We know when we solve a squaring equation, we have to be on the lookout for that little exponent. It's reminding me, hey, look out, there might be 2 answers, right? When I undo a squaring, I have to consider both the positive and negative square root. So if I do the forward steps, cover up the equation, my first thing would be squaring. My second thing would be multiplying. My third thing would be subtracting, which means my solving steps. My first solving step would be, Isabel? Plus 5. Then divide by 3. And lastly, the positive and negative square root. Let's do it. We're almost there, guys. Hang tight. First step, plus 5. That gets me to 18 equals 3x squared. Next step, divide by 3. So we divide both sides by 3. That gets me to, go gadget arm, 6 equals x squared. And yes, the moment you've all been waiting for, what undoes squaring? The positive and negative square root. How many answers? 2 answers. How do I get them? I consider both the positive and negative square root. That is to say, if x squared equals blah, then x is given by the positive and negative square root of blah. In this case, 6. Sometimes it will reduce, sometimes it won't, but either way, I've got my 2 different answers. I've got my arrows, I've got my split. In the first case, x is equal to positive root 6. In the second case, x is equal to opposite root 6. How many answers? 2. Pretty sweet. All right, ladies and gentlemen. Now, printable. I'd like a written response for each. I'm going to go ahead and give you a minute and a half, which will give us a minute and a half to share. So a written response for each, and then we're going to come back and share it together. The collection of all inputs, don't say it out loud, please write down, is called the what? The collection of all outputs is called the what? If you need to check back in your notes, that's totally fine. Please don't call out though. I'd like a written response from everybody, and then I'm going to call on you to share. Okay, the collection of all inputs, right? What is the collection of all inputs called? Kaylin? The domain. Raise your hand if you have the same as Kaylin. The domain. Domain. Keep it up if you have the collection of all outputs. What's that called? What's that called? Thanks, hands down. Emma? The range is correct. The correct collection of all output values, or y values, is the range. Good. In this expression, what's the independent variable? Haley? M is correct. It's inside the parentheses. That's my independent variable value. That's my input. It's inside the parentheses. The output then would be G or G of M. Would be the output values. And then argument is a fancy name for input again. So argument is still M. Argument is just another way of saying the input value. And lastly, just in time, P maps 9 onto the square root of 4 times 9 minus 5. Order of operation tells me that's the square root of 36 minus 5. So my final answer, fully simplified, would be the square root of 31. Don't change it to a decimal. You lose accuracy. The square root of 31 is exact. Once you put it into your calculator, it spits out a decimal, and it cuts it off. Right? An irrational number goes on forever, so this is the preferred form. It's nice and compact and exact. Katie? What is it? Signatures? Ah, we can't now because I'm too late. Sorry. Next time. Have a wonderful day, ladies and gentlemen. Strong work today. Make sure you do your reading questions first and follow your assignment sheet.
Wait, who's in this spot? Yeah.